My name is Michael Silberbach, and I want to tell you about personalized valves that we have designed that may be valuable to the Turner syndrome community. Just to briefly begin, I think I don't need to tell this audience the significance of the bicuspid aortic valve in Turner syndrome, but I'd like to take a moment to point out a few things that maybe nobody has really thought much about. Here we have the normal configuration looking from below of the aortic valve with three symmetrical and equal sized leaflets. And down here we have a typical bicuspid aortic valve, which we often call the left-right fusion type. But the thing I want to point out to you is that, and which people don't pay much attention to, is the asymmetry of the aortic sinuses, this housing that surrounds the valve. And this is quite typical of bicuspid aortic valve with two small sinuses and one large sinus, even though there are only two functional leaflets. And the problem is that, these valves often thicken and need to be replaced. And we got the idea that it may be the shape of the aortic sinuses may be critical in the nature of the flow that comes out of these valves, particularly when they're replaced by a surgeon or an interventional catheterizer. So if you could imagine if typically when the surgeon or the cardiologist goes in, they go over the shelf and they put in a symmetrical valve. But what would happen, and this probably happens to everybody who has this type of configuration, they'll put a symmetrical valve into a situation where there are asymmetrical sinuses. And we hypothesized that the result of that would be very abnormal flow downstream of the valve and may also lead to the early senescence of the valve itself. So we invented a new kind of valve that I want to tell you about. So just to put this in the context of Turner syndrome, bicuspid aortic valve, as many of you know, is the most common congenital heart defect. And in the overall population, it occurs in 1% of males and about half that number in XX females. But if you take that 1.5% and consider there are 8 billion people in the world, that would be about 15 million people that have bicuspid aortic valve. And then if we look at Turner syndrome, 25 to 50% of individuals with Turner syndrome have a bicuspid aortic valve. And so that would lead to about, well, if you think about it, if that's 15 billion people, 15 million people would have a bicuspid valve in the world. But if 25% have, there are many more. If all of them had Turner syndrome, there would be a huge burden of bicuspid aortic valve. And it is a large burden in the Turner syndrome community. This is just a depiction of the various forms of bicuspid valve aortopathy, this being normal, where the aortic sinuses are symmetrical and there's an equal size of the arch of the aorta. Here is the view of a typical Turner syndrome aortopathy aorta, this tubular form where the ascending aorta is hugely dilated. And what is it that causes that dilation? And it's some kind of injury to the wall in the setting of abnormal tissue that makes it bulge. And as you know, in catastrophic situations, burst and so-called dissect. So we are very interested in how the flow might be affected if we put matching valves that match the shape of the aortic sinuses. And so I'm asking the question here, what does an Urban Outfitters sale have to do with aortic wall stress? And I'm going to show you this little video from YouTube. And can you see what I'm showing here? So there's a bunch of people excited about getting into the store with this tremendous sale. And oh wait, what happened there? there. So what you're going to see is, I got to get past this little advertisement. And what you're seeing is a bunch of people that are standing outside. This is the door here, and this door is going to rise up, and there's a bunch of people, and they're murmuring, and they're very quiet. And then as we move along here, as the door begins to open, there's a cacophony of people, and the energy is just building, and they're bumping into each other. This is sheer stress within the crowd of people. Now, as this door opens, they're going to, the noise will become deafening, and they start to run through this door, and you're going to see that as well. And I want you to imagine something, because it'll be important for a video that I'm about to show you. If we put little lights on all these people's heads, and then we turned off all the lights in the room, we would see streamlines of all those little heads as they move through this door, as they rush with great excitement and energy through the door. So we're going to watch that. Here they go. They're screaming. They're screaming. Here comes the doors going up, and look at them run. Okay, and right here, I want to point out something. There's a post here. And if you'll, I'm going to keep it moving along, they start spinning around the post and hitting with the shoulders. So this is sheer stress within the vessel of the aorta. But what's happening along this post and at the edges of this opening valve, if you will, a lot of turbulence and disrupted flow of, in this case, urban outfitter, exuberant buyers at this sale. But we're going to think about that as what happens when flow is made or abnormal as it moves through a valve. So there they go. See them bumping into that post and how they're spinning. And then they start speeding up, but they're going very slowly through here as the energy gets absorbed by the wall and these obstructed things in their way. So I know that's kind of an unusual analogy here, but I think it's quite appropriate for what we're talking about. And so here is an aorta from a 43-year-old woman who has bicuspid valve aortopathy with this tremendously dilated aorta. This woman doesn't have Turner syndrome, but this is very typical of the aneurysmal aorta. And here is our valve placed in the sinuses of this person who has this very typical asymmetrical aortic sinuses. And here is the experiment that we did. We did a flexible 3D print of this individual's aorta, and then we made a valve using our patented technique, and we've placed a valve that reflects the shape of the aortic sinuses, one large sinus and two small sinuses, just like I showed you in that first picture. And this is one experimental design. This is our test. And this is our control design. We took that exact same aorta, but instead of putting a matched sinus, matched valve with the matched large sinus and two smaller valves with the two small sinuses, we put a symmetrical valve into this exact same aorta. Note that there's a large sinus and two small ones, just like I showed you. And then this is a bioreactor that's all made out of plastic, because we're going to put it into an MRI machine that has 30,000 force of gravity. So there can't be any metal on there. And there's some tubes here that go out to our control room so we can pulse and make the simulation of the heart circulation. And the two valves, the same aorta with the control and the test valve are inside there. And then we look at something called 4D flow, and that's what I'm going to show you next. So here is both of those aortas, the one that was in my right hand here. This is the matched situation where they're asymmetrical sinuses and asymmetrical leaflets. And what you see here is like just if you were imagining little lights on the head of all the people running into the sail, the flow in this situation is moving very straight and symmetrically through the valve, which is right here. It does hit this far part of the wall. But compared to that to the mismatch situation, the one that the surgeon and the interventional catheterizer might use, the flow going through there is quite different. Right when it goes through the valve, it heads immediately off to the right, then it spins around 180 degrees, hits the wall, and goes flying with high velocity, creating a great deal of shear stress, which creates an injury in this wall. And this is saying that if we used matched valves to the asymmetry of the sinuses, we can reduce the wall shear stress or the injury occurring in the wall by 30 to 50%, which is quite a significant improvement in the function of the valve and the effect it might have on the downstream aortopathic aorta. I'm just pointing out where this wall shear stress is occurring. So just to briefly show you how we make these valves, we create molds also from MRI and using a 3D printing technique, a positive mold and a negative mold. And then we use some kind of tissue. It could even be stem cell derived tissues. And the surgeon would, or the interventional catheterizer could push it into this negative mold and then put the positive mold on the outside and then snip away. So he's got a leaflet that is reflecting the shape, in this case, of the larger sinus. Now here's the actual, box cutter, we call it, this device that the surgeon or interventional catheterizer will use. This is the one that will make the large valve leaflet, and this will make the two smaller leaflets, and then it could put in an armature and then placed into either a delivery device in the cath lab, or the surgeon can then put it into the aorta. So, what we're doing now is, experiments to validate this concept of improved flow through a pathological valve. And these are technicians, and the hope is in the future we'll have a patient, a child, who gets this type of valve, and it may provide great longevity to the valve itself, reduce any injury to the aorta beyond that. So that's our project. We're pretty excited about it, and really want to thank everybody that's helped us with this project. The Turner Syndrome Society of the United States, of course, the Ravel Pittman Fund for the Turner Syndrome Society, our own institution, the Friends of Dornbecker, and the Dornbecker Children's Award that I received to work on this. So that's what I wanted to tell you, and thank you very much. And I will be happy to take any questions.